In this second video for the lecture, we're going to consider the question, what is information? Now, you've just done some activities there where I asked you to tell me, and also we talked about the game about information, guess who, when you have to guess the player that another person has, or they have to guess the player that you have by asking yes, no type of questions. We're not going to do that here though, you've done that in your activities. So instead, we're going to start focusing on the quantitative answer to that question of what is information. So let's look to what information theory is here. Information theory is an approach to quantitatively capture the notion of information. Now, traditionally, information theory comes at this question of what is information by providing answers to two fundamental questions. Firstly, what's the ultimate data compression? That is to say, how small can we zip up a given file? How much can we press it? How much can we compress it? How much information is actually there? The second fundamental question information theory asks is, what is the ultimate transmission rate of communication? So what's the maximum download speed I have of over my telephone line at home, for example? Yet information theory is about far more than these traditional answers. We can see that in this picture here from Carver and Thomas, where we can see how information theory is used to answer questions in physics, in mathematics, in economics, statistics, and as well as the traditional area of communication theory. Now, my research area about how complex systems process information, which is obviously strongly related to the topic of this course, kind of fits in here somewhere between physics and computer science, or you can think about it as not between but across both. So let's start defining information. We'll take our first pass still kind of from a qualitative perspective. I like to say that information theory is all about questions and answers. We can think about information as being the amount by which one variable, which could be an answer itself, it could be a signal, it could be a measurement. It's about how much that variable reduces our uncertainty or surprises us about another variable. Okay, so there's some key words here I want to pick up on. Here we're talking about how one variable reduces our uncertainty about another. So we've got two variables here, and that effectively becomes our question and answer. There are two variables, a question and an answer referred to two different variables here. We've got the key words uncertainty and surprise, and we've got information. And for information, we talked about a reduction in uncertainty or surprise. So we're going to drill into those key terms more very soon. So you'll see here that we need to quantify both uncertainty as well as uncertainty reduction. Here we're going to quantify uncertainty using entropy, our fundamental measure of information theory. And uncertainty reduction is what we will call information. So this is why I refer to entropy and information, uncertainty and uncertainty reduction, as two sides of the same coin. And you'll hear me saying that much more often. Claude Shannon, the founder of information theory, quantified these concepts and made such quantitative analysis possible. Okay, importantly, we normally measure information in bits. One bit refers to the amount of uncertainty about an equiprobable yes or no question. Does my coin flip give me a head or tail? Is the next person to walk through the door a male or a female? Well, the answer to that question provides one bit of uncertainty reduction or information. As I say, uncertainty and uncertainty reduction or information are the two sides of the same coin. So here the examples could be what's the result of my next coin flip, or what's the sex of the next person walking through the door. Once we know the result, that provides us one bit of uncertainty reduction to the one bit of uncertainty that we had about that question before we got the answer. To quantify this precisely, we need to go through some preliminaries. So here we're going to be talking about a random variable, capital X. This is a variable whose value is subject to chance. It could be an answer to a question, a signal, a measurement, the result of a coin flip, whether it rains today, and so on. We will use lowercase letters, here lowercase x, to represent a sample or an outcome or a measurement of x, a specific realization of our random variable. Our realizations are drawn from some discrete alphabet. Here we can write this very mathematically as the set of realizations x1, x2, and so on. For example, for a binary x, our set of realizations could be zeros or ones. For a coin toss, we can represent this as heads or tails. For hair color, and guess who? What would that be? It would be the set of blonde, brown, black, grey, and red. I think from memory are the 5 possible hair colors in Guess Who. Now, importantly, we have a well-defined probability distribution function over this outcome space, and we represent that by P of realization little x, which represents the probability that a random variable takes this specific value. And this is defined for all the realizations in our realization space. Obviously, each realization has a probability that is on the interval 0 to 1 inclusive, and that's defined for all of our possible realizations. And when we sum the probability values up for each realization, obviously, they have to normalize to give us 1. In everything that we'll look at here, at least from a theoretical perspective, we are assuming that we have these probabilities defined exactly, that they're defined correctly. That's important. We're not going to talk about estimation errors at this point. We'll talk about that later on. Okay, the fundamental quantity of information theory then is what's called the Shannon information content. This refers to the information content of a sample or outcome, a specific sample or outcome, little x, from our sample space. It is simply the log of the inverse probability of x. This is our Shannon information content. Here, the units of Shannon information content are in bits for when we take the log in base 2. But we don't have to. We could take the log to a different base. We could take it to base e, in which case we call the units nats, short for natural units. But what is the Shannon information content? It's a measure of surprise that we have at the value of this sample or outcome. So when we read the outcome that we got this time, how surprised are we about that outcome? So the information content is a measure of the surprise at this value or outcome. How surprised are we when we see this specific value? Our surprise is always greater than or equal to 0. We can't be negatively surprised. We can have 0 surprise. If we get the same value all the time, we have no surprise when we see it. And we can actually be surprised if it's something we're not sure if we're going to see or not. So to be more specific, as I say, if there's only ever one outcome, if only women ever walk through this door here, and I ask the question, is the next person to walk through a man or a woman? I'm not going to be surprised at the next realization that I measure because it has to be a woman. There's no surprise there. However, there is always some level of surprise if there exists more than one outcome with a non-zero probability. So if it's possible that either a man or woman could walk through that door, I will always have some level of surprise when I measure the next sample of that process. Always. Even if it's overwhelmingly likely that it's going to be a woman rather than a man. If the probability of a woman walking through the door is 0.99, there's a 0.01 probability that it's a man. As long as it's possible that it's something other than a woman, I will still have a small level of surprise when a woman walks through the door. Okay, that's an important concept. What is important also is that our surprise increases as x becomes less likely. So on that example there, we may have a very skewed probability that it's highly likely a woman walks through the door with, say, a 0.99 probability and only a 0.01 probability that a man walks through the door. So for that realization of a man walking through the door, I am very, very surprised when that happens. And my level of surprise increases as that outcome becomes less and less likely. The less likely an outcome is, the more it surprises me. After this, we have some activities that I want you to do with the Shannon information content. So do look at the activities on the learning pages there to continue.